And we're back. All right, so heat movement. Earlier, we talked about the law of conservation of energy and how it states that heat energy cannot just appear out of nowhere and disappear to nowhere. If an object warms up, that heat had to be absorbed from somewhere. And if an object cools down, that heat had to be given off to something. Okay, so when you have ice in your hand, it's melting because it's taking the heat from your hand. That's why ice feels cold. Okay. Um, if you have a hot cup of coffee, all right, the reason it feels hot is because the heat from the coffee is warming up the mug, which is warming up your hand. All right. Um, and again, it's because your hand is cooler than the hot coffee, so it's traveling from hot to cold. In the Earth's ecosystem, heat is gained by the sun's radiation and given off to space at night. And this is why a cloudy night is typically warmer than a clear night, because the heat gets trapped in by the clouds. All right. Um, yeah, I don't know if you've ever noticed that, but that's why places like the desert could be extremely hot during the day, but can get really cold at night. Like even in the summertime, you still need a jacket at night because there's no clouds, so the heat just escapes. All right, but when you're in a place that's more humid, again, like we talked about earlier on the beach, okay, you have more humidity in the air that holds on to the heat um, and keeps the temperature more constant. Okay, I don't think this works. Yeah, so we'll go to the next one. All right, heat can move from one object to another in three ways. You have radiation, convection, and conduction. Okay, we'll talk more about those in a moment, but just to kind of explain this picture, right? Radiation is what's coming off of the fire, so squiggly arrows. Okay, the sun's heat is radiating for us, okay, meaning you're not touching the sun, but you're still feeling the heat. You don't touch fire, but you feel the heat from the fire. So anytime you feel heat from something, that is radiating the heat. Okay, convection is when you boil water, you're heating, like in this picture, you're heating the water molecules that are on the bottom. Okay, well, hot water rises. So when you heat up the water on the bottom, it goes to the top of the pot, and then when it cools back down, and then it comes back to the bottom. And so it's just a circulating of, as the water warms up, it rises to the top and it pushes the other water back down. So it's circulating that. So convection is the circulation of heat. It's kind of like what happens to air conditioners, okay, and heaters. Have you ever noticed, like, or not necessarily around here, but if you're from up north or you've ever been in the mountains, a lot of places have heaters in the floor. Okay, they have heaters in the floor. A, keeps your feet nice and warm when you're walking around. Okay, but B, hot air rises. Okay, but here in Texas, where we focus more on air conditioners, okay, you don't see air conditioners on the floor. You see air conditioner vents in the ceiling, okay, or close to the top, right? And that's because cool air sinks. Um, and same thing with cars. That's why a lot of the vents are up high. Well, other reasons for cars, but cold air sinks, warm air rises. That's convection. And then the last one, conduction, that's when you touch something that's hot. Okay, so like the hand on the handle is hot, so it's burning the hand. Okay, so again, conduction is when you physically touch something and it is hot. All right, so let's dive into those definitions. Okay, the energy from the sun reaches Earth by radiation or electromagnetic waves. The infrared part of the electromagnetic spectrum is heat in the form of radiation. Let's see. So heat from fire, heat from light bulb, heat from coil on the electric stove. Again, anything that you're not touching but you feel the heat coming from it is a radiation heat. Then we have convection, that's the movement of heat by circulating materials. So anything that's a fluid, like gases and liquid, can move heat by convection and often called convection currents, okay? And like I talked about, this most air conditioning systems, the ocean currents work this way. Warm and cold fronts, okay? Have you ever noticed that cold fronts come from up north, like Alaska, Canada, the polar vortex that we had during the storm? Okay, that all came from up north and then was pushed down south, right? Whenever we have heat waves, okay, you're never like, oh, here comes a heat wave from Canada. No, heat waves generally come from the Gulf of Mexico, all right, or just Mexico in general, and push up to towards us, okay, because the heat's rising towards the North Pole, all right. So if you ever watch the weather, I know people don't just sit and watch the news very much anymore, but if you ever do sit and watch the news, listen to the meteorologist and they'll talk all about the fronts. Okay, cold air comes from the north, hot air comes from the south. Conduction is the movement of heat objects that are touching. Most common form of heat movement is when cooking, because you have the pot on the stove, so the pot's touching the stove, heating it up, right? That's what this says. The food touches a pan, that's touching a burner. As the pan absorbs heat from the burner, the food absorbs heat from the pan. All right, it's just a big domino effect. All right, again, but conduction, they have to be touching. When you touch a hot pan, heat moves, from the pan into your hand, which then burns you. Often the lasting effects of a burn can be minimized if you can quickly get the heat to move out of your hand by running cold water over your hand for a long time. All right, because again, heat moves from hot to cold. So by running cold water over the burn, it's pulling the heat out of the burn. So you're still going to have some damage, but it'll be less damage. And says for a long time, 5 minutes minimum. Your goal is about 15 minutes because it takes a while, because water is not like a metal. It takes a while to draw the heat out, but it does, and it does it slowly and safely. So if you ever burn yourself, find a cool source of water, run that over the burn part. Heat energy will always naturally move from an object with higher heat to an object with lower heat, regardless of the method of heat transfer. All right, and again, so convection, conduction, and radiation. The law of conservation of energy also tells us that the amount of heat lost by the object must be equal to the amount of heat gained by the cold object. All right, so that's what we did earlier with the two different blocks. Okay, A lost 5 degrees, B found 5 degrees from object A. So hot becomes cooler and the cold becomes warmer because the heat lost, remember Q stands for heat, so the heat lost is equal to the heat gained, okay? So remember, negative means that something's getting colder, positive means that something's getting warmer. Sometimes when an object gains or loses heat, it is not just the temperature that changes, but the phase of the object can change. The phase depends on how much heat energy is in the object, and it's often measured by temperature. Solid will have a lower temperature than the liquid form, which will have a lower temperature than the gas vapor form. All right, so this is an energy and states of matter diagram. If something has high energy and velocity, then it's going to have low attractive forces and density, and a high temperature. Okay, if something is low energy and velocity and a low temperature, then it's going to have high attractive forces and density. Basically what that's saying is gas molecules don't want to be around each other. They're floating as far away from each other as they can, all right? They have the most energy. Solids are all packed tight next to each other. They don't move. They have the lowest amount of energy. So to get from a solid to a gas, okay, you have to gradually increase the energy, so then it becomes a liquid where it's moving around more, and keep increasing energy, and now it's moving around as a gas, okay? When the gas releases energy, okay, then it becomes back to a liquid. And when you keep losing energy, then it's back to a solid, okay? So as you're taking in energy to go from solid to gas, that's an endothermic reaction. As you're losing energy, that's an exothermic reaction, okay, as it's cooling down, or not cooling down, but yeah, it's losing energy. Phase changes occur when sufficient heat energy is added or removed, okay? The positive Q is heat added or absorbed, okay, so it's an endothermic reaction. And negative Q is heat lost or released in this exothermic reaction. From this heat curve for water, we can see how the temperature changes and the phase change. Notice that the temperature doesn't change during the phase change, which is the two flat lines. Okay, so like at the bottom left, where the first thing is, okay, that's ice. As the ice is heating up, so it's increasing energy, all right? Once it hits the melting point at 0 degrees Celsius, the ice is going to stay 0 degrees Celsius until all of it's melted. Once all of the ice is melted into water, then the water temperature starts increasing again. Okay, remember, heat loss is equal to heat gain. So as the ice is melting, the water is starting to increase temperature, but you still have the cold ice, so that's why it stays 0 degrees. Okay, once it's all liquid though, it starts adding more heat to it, okay? And then when you get to 100 degrees Celsius, the boiling phase there, right, the water's starting to evaporate, all right? And as it's evaporating, that stays 100 degrees. And then once every drop of water has evaporated, now the gas can start increasing its temperature as well. All right, so again, the phase changes as it's melting from solid to liquid or evaporating from liquid to gas. The temperature stays constant until every piece of it has changed phase. All right, next we're going to talk about heat and chemical reactions. So thermochemical equations is a balanced chemical equation that includes all physical states like solid, liquid, and gas, and change in enthalpy or the heat content. Remember, Mr. DeWitt talked about it in the video that you watched last week. Nope, not last week, earlier this week. All right, so heat can be written as either a reactant or a product. And every chemical reaction involves a change in energy, whether it's heat or light. Every chemical reaction has something. Sometimes you can feel it, sometimes you can't. All right. Let's see. If a chemical reaction feels cold, that means it's absorbing heat. Okay, because as you're touching it, it's taking the heat from your hand. This is an endothermic reaction. It's taking the energy in. Heat energy is written on the reactant side, so the Q is positive. Okay, so you're adding heat again, so the energy will be on the reactant side. If a chemical reaction feels warm, that means it's giving off heat. So it's an exothermic reaction because the energy is going out of it. The heat energy is written on the product side, but the Q itself is negative. I know it's not a negative number in the equation here, but because it's on the product side, it's assumed to be negative as it's being lost. With endothermic, okay, remember it's adding a reactant. The heat flows into the system from the surroundings. And Mr. DeWitt talked about the system and the surrounding. The system is wherever the reaction is taking place, and the surrounding is what you're adding to it. Okay, but I talked about this before. This is why your skin gets cold when you hold ice. The heat is flowing out of your skin to melt the ice. Right, so the system is the ice and the surrounding is your skin because that's what's being affected by it. Exothermic is the product, so on the right side of the arrow, the heat is released from the system and it's absorbed by the surrounding environment, which is why it's used in the instant hot pads. Okay, the iron and oxygen is used in the hot pads because whenever you take it out of the package, you've exposed it to the oxygen, the iron to the oxygen, and that creates an exothermic reaction. So the system is the hot pad, and the surrounding is your skin because your skin is what's absorbing that heat. All right, so enthalpy, which is represented by the letter H, again, Mr. DeWitt talked about that too, is the total heat energy of a system. All right, so the delta or the triangle H is talking about the change in enthalpy. If it's exothermic, the change is going to be negative because the energy of the system is decreasing. And if it's endothermic, then the change of the heat is or enthalpy is positive because the energy of the system is increasing. So an example is to separate water into hydrogen and oxygen, or electrolysis. Electricity is often used, right? So is electrolysis of water endothermic or exothermic? And it wants to know where the energy goes in the equation. Okay, so you're adding energy to make the water break apart. Okay, so when you're adding energy to it, you're adding that electricity. This goes on the reactant side. So this is an endothermic reaction because you're adding energy to it. The enthalpy of reaction can be calculated to determine if heat is released or gained. All right, so you're going to be using your star chart for this section. The change of enthalpy is equal to the final, or to the amount of enthalpy in the products minus the amount of enthalpy in the reactants. All right. Let's see. If the change of enthalpy is positive, then heat is absorbed, so it's an endothermic reaction. If the change of enthalpy is negative, then the heat is released, so it's an exothermic reaction. All right, so yeah, we'll use the star chart. This is some values from the star chart to find the change of enthalpy for liquid ethanol undergoing combustion. And then it wants to know if it's an endothermic or exothermic reaction. So I'm going to flip to writing this out by hand. All right, ready? All right, so we're going to solve an enthalpy problem. All right, so we got a combustion problem here. So carbon, hydrogen, and oxygen coming together to make carbon dioxide and water. Remember, with chemical equations, we have reactants on the left side of the arrow, and we have products on the right side of the arrow. Okay, for enthalpy problems, you're always going to be provided with a chart like this. Okay, the compounds will be different, the numbers can be different too, but you'll have what you need. All right, so our job is to figure out, is this an endothermic reaction or an exothermic reaction? We're going to take these values, we're going to plug them in to each of the problems, or plug them in where the compound is. Okay, we're going to add the reactants together, we're going to add the products together, and then we're going to figure out the difference between them. In the end, if our number is positive, it's an endothermic reaction. If our number is negative, then it's an exothermic reaction. Okay, so again, we're going to plug in these values. So we have just one of these. So I'm going to say for my reactant, we're going to do negative 277.69 plus, we have 3 oxygens here. So I'm going to do 3 times oxygen's number, which is 0. So 3 times 0. We're going to add those together to see what we get. Okay, I'm going to do the same thing for my products. So here it says I have 2, so 2 times carbon dioxide, which is negative 393.509, plus 3 waters, so 3 times the water's number, which is negative 285.830. And we're going to add that together. Okay, so I've already done the math to kind of save some time. So here we have negative 277.69 plus 3 times 0. Well, anything times 0 is 0, so this one stays at negative 277.69. All right, here 2 times carbon dioxide's number plus 3 times water's number gives us negative 1,644.508. Okay, so this is my number for my reactants. This is my number for my product. To figure out if it's endothermic or exothermic, we're going to do product total minus reactant total. Okay, it is always product minus reactant in that order. Okay, so my product is negative 1,644.508 minus negative 277.69. All right, and again, I've done this math for us. We get negative 1,922.2 kilojoules of energy lost, okay, because it's a negative number. So this is how much is lost during this reaction. Okay, remember, if it's negative, it means that it's exothermic. Okay, so we just figured out that during this combustion reaction, it loses about 1,922.2 kilojoules of energy. Again, the negative number tells us that it loses. If this had been a positive number, that would mean that it would be gaining energy, and that would make it endothermic. So we do all of this math to figure out, is it gaining or losing energy? Remember that these numbers will be provided to you. You have to know how to plug them in to the equation, okay? You're literally plugging the numbers in to where the compounds are, multiplying if it has a number, a coefficient in front of it, get the totals, always product minus reactant. Okay, so let's go ahead and finish up these notes, and then y'all can get started on today's assignment. So the last thing I want to talk about before we're done with the notes is an additional way to show a change in enthalpy without a calculation is with an enthalpy diagram. Mr. DeWitt touched on these with the video that you guys watched. All right, so here we have an exothermic reaction and an endothermic reaction. With exothermic reaction, remember H is talking about the enthalpy, right, or how much energy is in the system. Okay, so reactants have a lot of energy. If the reactants start with a lot of energy and the products don't have a lot of energy, that means that after a short burst of energy, it's lost. Okay, so the change of enthalpy is negative because the reactants are more than the products, or the products are less than the reactants. Whereas endothermic is the opposite. The reactants don't have a lot of energy in the system to begin with, but they finish with a lot of energy in the products. Okay, so it's positive because it's adding the enthalpy. Okay, so make sure that you're familiar with these graphs because you will be seeing these kind of questions on the test and on the quiz and on the assignment. All right, so the key to knowing if the diagram shows an exothermic or endothermic reaction is energy going in or is it going out? Okay, with exothermic, energy is going out. That's why products are lower. With endothermic, the energy is coming in. That's why products are higher. All right. So that's what you need to know for this thermal unit. I hope you guys have an awesome day.